I'm really happy to introduce Professor Crockett. She received her bachelor's degree from the University of Denver in 2002, and then went to University of California, San Diego, and achieved the master's degree and a PhD in 2007, and joined the faculty in our department later that year, becoming the first female faculty member in the College of Engineering, BYU. She has expertise in fluid dynamics and specifically focuses on two areas of research. One is on internal waves in the ocean and the atmosphere, and how these affect global oceanic and atmospheric flow patterns. And the second is on superhydrophobic surfaces, which she'll introduce and talk about here. She enjoys playing all kinds of sports. And if you dare compete with her, you need to bring your game face. She played collegiately volleyball at the University of Denver, and she loves volleyball and basketball, and she'll play with anyone that dares lace up their sneakers and get on the court with her. Recently, another research group in our department made the mistake of challenging the students in our joint lab and us a volleyball match. And this was a big mistake. Not because anything the students did, but because Professor Crockett was a one-woman wrecking crew. Recently, she's taken up jumping out of airplanes with a parachute, and she enjoys spending time with her family. She currently teaches the young women in her ward, and she fears that they're sick and tired of hearing about why they should all become engineers. She's an excellent scholar and a top-rate teacher, always among the highest rated in our department. And I thought I would just share, before I turn the floor over to her, one comment that a student made recently. Quote, "Dr. Crockett is amazing. Her lectures are very engaging and interesting. I never even thought once about sleeping through her class." I hope we'll do the same.
Thank you so much, Dr. Maines, for that introduction. And I do hope that none of you guys sleep through this. I'm actually really excited to take you on this journey. I basically get to talk about whatever I want. So hopefully you'll learn something and have a little bit of fun. And those generally should go hand in hand, as my students know. All right, so you've already seen a video about Alice Louise Reynolds, but I just wanted to put in kind of my 2 cents. As I learned a little bit more about her, I was very impressed and with her clear dedication to unselfish service and lifelong learning. And I'm very honored to receive this lectureship in her name. She was very impressive what she did for the library, collecting the volumes, and her advanced study. I just very much appreciate this opportunity, so thank you. I also definitely need to acknowledge the lab. Our research lab includes a few professors, and lots of graduate students have been listed here, lots of undergraduate students who do amazing work, and you'll see a lot of their work today. All right, and so there's a picture there with a few of us. It's not everyone, but this is the group, and they do wonderful work. And the National Science Foundation and NASA also sponsor some of our research. All right, so today's focus is going to be superhydrophobic surfaces, as you saw on the poster, which is probably why you're here. And I want to take you through understanding what they are, how we create them, and then take you to the kind of the state of the art right now of what we understand about these surfaces and why they're important and how we can use them. Then I'll talk about the latest research going on in our lab, which has to do with boiling water droplets. And in blue there is written the Leidenfrost effect. So if you don't know what the Leidenfrost effect is yet, I'll teach you about that and how that's different on our surfaces versus maybe the regular types of surfaces you're used to seeing. And then we'll do bouncing and boiling water droplets. And we'll talk a little bit about atomization. So again, if you don't know what that is yet, I'll teach you about atomization and then how that occurs on superhydrophobic surfaces. Before we can really get into this, a real quick reminder, hydrophilic versus hydrophobic, right? So if it's been a while since you took high school physics, hydrophilic is a water attracting surface. So if you put a water droplet on it, it's going to spread out, and you can see here that basically the water drop is more attracted to the surface than itself. So it's all about a surface energy idea. And a hydrophobic is water repelling, so it's more attracted to itself than the surface. All right, so then super hydrophobic, if you need something that's not just water repelling but is super water repelling, right? I know very scientific terms here, like this leaf, where as more water falls on it, if it sticks to it, it will eventually be have too much weight on it and break. Or on the upper right, that's the blue Morphodidius butterfly. And that butterfly has to very quickly shed water so it can continue to fly. And while it's shed, it actually also needs to have dust and other particles and debris removed from its wings so it can continue to fly. The Namib desert beetle, as its name suggests, is in the desert and is able to collect water out of the air by condensing it on its superhydrophobic back and guiding it to its mouth. All right, so how do all of these work? Well, the idea is instead of it just repelling water, so if I take a hydrophobic surface and I give it a microstructure, and we'll look at a couple more of these, the idea is if I just give it a microstructure, really small scale, a water drop is going to sit on top of it. So now it's not just unattracted to the surface, it's also not attracted to the the air that's in the cavities beneath these gaps. And so it beads up even more, and we call that super hydrophobic, right? So if it starts to bead up and gets close to an actual sphere, that's a contact angle, as you see here, that theta of 180 degrees. And we can get surfaces that are 179-degree contact angles. And this is called the Cassie-Baxter state. That's when it sits above the structures. What this looks like on a lotus leaf is shown in the bottom left here. This is an image of, well, clearly zoomed in, a microscopic image of a lotus leaf. And you may not have a good feel for what 10 microns is. So I want everyone to look at their fingernail really quickly. The thickness of your fingernail is about 350 to 400 microns, right? So not very thick, but this scale here is 10 microns. So these little nubs are 10 microns. So take your fingernail, slice it 40 times, and then that's how big one of those nubs is, right? So these are very, very small, and that's why we call them micron scale. And then if we zoom in further on the middle picture there, you can actually see it looks almost like it has a hair-like structure on it. And that's zoomed in even further, and those are nanoscale structures. So this is a two-tiered structure, we call it, that has both micro and nanoscale structures. And the water will sit on top of both of those and bead up almost completely into a ball. But the idea is you need one of these, or both is fine, in order to get a superhydrophobic surface. You need the microstructure and then the hydrophobicity. And in the upper right, you can see the butterfly, and it actually has they look like scales, kind of, and then on those scales, it looks like they have cuticles. So that's their microstructure. So it's a little bit different, but the idea is the same. It's sitting on top of this microstructure. Hopefully these pop up. There we go. So what does this mean if we actually throw something at the surface? So this is just a drop impinging. Hydrophilic is on the left, so it's water attracting. So you can see that it just falls down and completely splats and is flat. But a superhydrophobic surface on the left here, the drop actually rebounds, comes back together, and can bounce up off the surface. And so this is dynamically very different between the two types of surfaces, smooth or with this structuring. Well, what if I do more than droplets, right? So what if I throw an entire bucket of water, right? So the guy on the left just has normal clothes on, and on the right, the clothes have been coated with a superhydrophobic spray. Right? So you can see this is very different, maybe not the best application, but you can see that it creates a different response to the mud. So I'm going to hand out a couple samples so you guys can play with this. I want you to still pay attention to me, but my wonderful nieces Carly and Taisley are going to hand out little Petri dishes. First thing I want to tell you, don't open them, all right? So in the Petri dishes is water, and they're taped closed, and they say do not open on them. But on the bottom is a superhydrophobic surface. It's been sprayed with something that repels water. And on the top, it's just the normal top. And so ideally, you kind of want to bounce it around and play with it and see how easily the water moves as you play with it and move it around. And you can kind of hit it a little bit harder up against the sides and make it break up. And as those droplets get smaller, they'll beat up even more, right? Because now gravity isn't affecting them. So I want you to kind of play with them and see what it looks like while you're still paying attention, of course. All right, so as you're starting to look at these, here's a couple samples of what a droplet looks like when it runs into something that's not flat, right? So this is literally just a tack poking through, sprayed with the same stuff that you guys are starting to play with now. And you can see that the water being more attracted to itself than the surface results in some really interesting dynamics. So you can see it almost creates something that looks like a toroid on the upper left. It just kind of rips in the middle and then comes together. And on the bottom right, when it's off center, the droplet starts to bounce and move in interesting ways. So it's really fun to kind of watch these surfaces. And since it's so fun, here's just one more real quick here. You can also have it fall on something that's like a blade. So I'm not sure if you guys have seen online, sometimes people talk about a superhydrophobic knife, all right? It's not really a knife, it's not really sharp, but if you look at the right there, if you just coat something relatively thin with this and then push it through water, since the water is going to be more attracted to itself, and so it almost looks like you cut this in half. How do we create these though? So in nature, obviously, they've already been very nicely created, but the way we make them is a few different ways. What you guys are looking at right now is a spray. So it's literally a spray you can buy at Home Depot or Lowe's. It's called Never Wet, and it's a spray. It has two coats. One of them is an adhesive coat, and then the other is a top coat that is hydrophobic and has little micro structures in it that kind of clump together, so you end up with this random clumping. That's why it looks a little bit frosty. It's not as clear as the top. The bottom is kind of frosty because it has these little micro clumps in there to give it that super hydrophobicity. There are other ways as well. I don't know if you guys know much about acid, but you can etch things with acid. So in the middle there, I'm showing you can do a hydrochloric etch on maybe a zinc sheet, and it eats it away. And so this upper left A is showing what happens when you etch this away. And it looks kind of like little mountains in there. And you can see the scale is 5 microns, so again, very small. And this will give you that microstructure necessary. Another thing you can do, though, you can take another step and put it in a water bath. And on the right there, it's now growing particles as well. And those are nanostructure. So this one, again, is a 2-tiered structure. You can do something like on the far right, where you have a leaf as a mold, and you make an inverse mold with something like a silicone, right? So you pour it over it, and then pull it apart, and now you have a new template, pour more silicone on it, and you can pull it up. So there are a lot of different ways to make these. And sometimes they are randomly structured, and sometimes in our lab, I'll show in just a minute, we actually give it very specific structuring. Some really significant issues right now, as you guys can see from holding the Petri dish that says do not open, is robustness, right? If you wipe your finger on that, it's going to come right off. Okay? Or it may leave behind oils if you just gently touch it. So they're not particularly robust right now. And then scalability is a problem as well. Most of the stuff we do is fairly small scale, right? So if I want to apply this to something really big, we'll talk about airplanes in a little bit, that starts to get a little bit tougher. So these are some issues that we have in the field right now. In our lab, we actually create these by etching silicon. So this is just a CD-sized wafer, or DVD. You guys probably don't listen to CDs anymore. And in the right is just a picture of our clean room, right? So in the clean room, we can create microstructures, and there's a lot of other types of stuff that goes on in the clean room. But we start with this wafer on the left here, and then we put a photoresist on it. And then we can expose it to light, and we can get really thin beams of light. And so we can get thin 10-micron beams of light, and then when we develop that, it eats away the photoresist right there. Then we put it in a plasma etcher, so it basically takes gases that are going to eat away silicon, and it does eat it away, except for where there's still photoresist. And I end up with this really nice structured surface shown in the bottom right here, right? So this is an SEM image, so a scanning electron microscope image of our surfaces. So you can see these really nice ribs here, and then they have cavities. And these are about 8 microns wide, and this is about 32 microns, right? So the total is like a tenth of your fingernail, okay? This is how we create our surfaces, but like I said, there are many other ways to do it, and there are advantages and disadvantages to each type of surface. right now I want to get us to kind of the state of the art, what we understand about these surfaces. So we started making these. They seem to repel water. This is great. Water beads up on them. But what's really going on that can actually help us to use these in some sort of advantageous way? And one of the first things is that droplets will actually roll. And this is different. If you think about the water on your shower door, right? It slides down, and eventually, if you're in Utah, probably leaves hard water stains. You got to clean those off, right? Superhydrophobic surfaces, literally the water will roll. So if you watch this closely, looks like I've got to start it again. If you watch this closely, you can see that the drop seems to, it's jumping a little bit, sorry about that video, but it seems to actually roll instead of slide. And it's actually picking up this dirt, basically, kind of a dirt, as it rolls, right? And so this is what the blue Morphodeus butterfly uses. It uses a superhydrophobic surface that it beads up, and then it also removes dirt. And so this is just a schematic in the bottom right, so you can kind of see what that looks like, that it's actually rolling and picking up dirt as it moves. There are multiple applications for this, right? So you can imagine never cleaning your shower again. That would be stellar. And other things in the upper right, you can see pouring ketchup out of a bottle, right? Ketchup out of your bottle, shampoo, anything that's in a bottle, basically getting everything out of it, right? And then other important applications, pouring chocolate on your shoes. Mostly it just looks fun. So another state of the art in understanding is drag reduction, right? So I want everyone to put your hands together. Just kidding. Okay. Rub them together. So if you rub them together, they start to get warm, right? Okay. So now I want you to put your fingers apart a little bit, so it's almost like you're interlocking, but keep them straight, and then rub them together. And how warm do your fingers get? Not really very warm anymore, right? So instead of rubbing up against another solid, you're rubbing up against air, right? And that doesn't provide much friction. They get warm because you have friction between your hands. They aren't warm anymore when you rub them against air because there's not a lot of friction associated with the air. And the same is true with a liquid and a solid. So now I have a liquid flowing over a solid and I have a lot of friction. But now if I have these gaps in there, as the liquid flows over the solid, I have these gaps of almost no friction. And we call that slip. That's why I call these slippery superhydrophobic surfaces. They slide along that gap and you get what we call slip. So the middle video here is a video of a hydraulic jump. It's on a hydrophilic surface, and I just have a jet hitting water. Okay, you can see this in your sink. You turn on your faucet and look at what the water looks like when it hits the sink below. And it will spread out in a thin film, and then it'll get a little bit thicker at the edge, and that's called a hydraulic jump. And what happens if I had instead a superhydrophobic surface here, that thin film would push out even further because there's less resistance to motion. So it can actually push out further and has more momentum. So that balance where I get the jump, so it's basically a balance of where gravity balances with the momentum of the outward coming jet, it will be pushed further out so I can have a larger thin film, which can help me with things like cooling processes if I have jet impingement cooling. On the right is a slightly different situation, but it's on a superhydrophobic surface, and you can see how different it looks. It spreads out, but instead of having this big downstream depth on the edge, it breaks up into droplets. So now we're looking at the combination of drag reduction and the water repellency, the lack of attraction of the fluid to the surface, and you can actually see the droplets start to bounce, and some of them even bounce vertically, so are removed from the surface. One of the applications for this, a common way to cool things that are very warm is with water, right? So it's easier to cool something with water than just with air. So I'll have a jet impinging, or I'll have a spray over here on the left. You can see it's spraying, it's just spray nozzles to cool something. This is just an image of a processor chip, but basically anything that's warm to get quick cooling. Right, so these are going to give you very different results, and if you use a superhydrophobic surface, then it's going to actually clean itself as well, so you don't ever have to deal with that. But we'll have a little bit different heat transfer, and I'll talk about that in a minute. That's really the newest and latest research. Another state-of-the-art idea is using variable hydrophobicity. Thus far, we've only talked about what if it's hydrophilic, what if it's hydrophobic. But you can also create structures that are both. So what we're looking at here is these, where you see the orange dyed water going, are actually hydrophilic tracks. right? And everything else is superhydrophobic. So you've made these tracks that are attracting water. But if you open them at the right angle, so as is shown here, right? So if you have this angle opening, the surface tension, the pull of this hydrophilic surface where it's attracted to water, is going to be greater than the pull on the skinnier end, pulling back on the water droplet. So this is a passive mechanism to get water to move, right? So you can see there's not a pump in here, there's nothing causing the fluid to move. It is only the difference in the structuring out here, which is superhydrophobic, and in here, which is hydrophilic. So this is a new, really just state-of-the-art, getting small volumes of fluid and moving them passively. And there you can do lots of different designs with this as well. The last one I'm going to talk about as far as where we are at the state of the art is condensation, right? So how do droplets form? Many of you guys have probably seen condensation like on the pop can in the upper left here, right? Well, what happens, you don't immediately just all of a sudden have a big droplet. It starts out as a fine mist. And what that fine mist looks like at a small scale and with these nanostructures, again, this is zoomed in, you can see a 50 micron scale, so I have a bunch of nano pillars here. And what we're looking at is tiny little droplets that are forming on those nano pillars. And that's condensation beginning. Those will start to coalesce and combine together. And when they do that, so here's two droplets, you can see them merging, and then as they become another droplet, they actually can jump, right? So you've probably never seen a square drop, right? Because the lowest surface energy is for it to be spherical, right? So if I take two drops that coalesce, they're going to try to go to the lowest surface energy. So they're going to come together and become a sphere. Well, that energy that they release by getting to their lowest energy state has to go somewhere. So it actually, when they come together, they bounce off the surface. That's the release of that extra energy. Okay? And so you can see that video in the right here. Now, hopefully makes a little sense. So here's the beginning of it. These two coalesce, and then it jumps. And you can see it actually jumps relatively high. It jumps a few diameters of the actual droplet above where it started. Applications for this, there are multiple applications, but one of the first to maybe think about is if I can't get water to stay on a surface, then I probably won't get ice to form on that surface, right? So on the left, those of you guys who've lived in Utah long enough or somewhere colder maybe have seen power lines that look like this, that have icicles hanging from them, all right? On the bottom left was a test that was done where the cables on the left were coated with a superhydrophobic surface and the cables on the right were not. And they were both allowed to have water droplets condense and freeze. And you can see on the left that it's not perfect. There's a little bit of frost in here, a little bit of drops on here. But overall, it looks nothing like this side where it has this ice layer and icicles coming off of it. Right? So this can be very advantageous. Also with airplanes, right? So I don't know if you guys have ever waited to get your wings de-iced. You're sitting there waiting and then they say, it took us too long, we have to do it again, right? So that would be great to never have to wait because the droplets never actually form. Now, this doesn't happen on every superhydrophobic surface. Some of them need some sort of mechanical vibration to help get that droplet off because initially they are tiny little droplets. You have to wait for them to coalesce in order to release that energy. And so sometimes they don't quite get there before they start to become frost. So there's also research going on with mechanical jolt or sending a current through them just to give them a little bit of a shake to remove those droplets. And so it's still very easy to remove them. You don't have to put a lot of energy in to remove them, but sometimes they need a little bit of help if it's really cold and they'll frost over before they coalesce. All right, so where are we in our lab? So we've done some of these things. You've seen some videos from some of the stuff we're doing, kind of state-of-the-art, why we study superhydrophobic surfaces and what we can do with them. But this is kind of the latest and greatest coming out of our lab. And so what happens when we heat the surface? Okay, so we kind of understand some of these hydrodynamics, water beads up, it rolls, but what if I'm trying to get heat into the surface as well? So if I look at this smooth surface on the left, this is what boiling looks like when I have a droplet. Okay, so you guys have probably seen when you're actually boiling water in a pan, what it looks like. You have what we call maybe, I think it's called a rolling boil, right? And so you have lots of vapor bubbles and things. Well, on a superhydrophobic surface, on a surface with just a droplet, that looks like this, right? So the droplet's kind of moving in all different directions, and it looks like it could be boiling. On the right, we have a superhydrophobic surface with a 95% cavity fraction. So that means 95% of what the drop is sitting on is air, right? So it's only in contact with 5% of the surface. And at 130 degrees, this is what it looks like. This is a video. This is what's happening. 130 degrees C and nothing is happening, okay? Well, what's going on when we put a drop on a superhydrophobic surface? Now the drop is sitting on top of all these structures, which is advantageous if we're trying to remove a droplet. But if we think about heat, I have a couple forms of heat transfer drawn on here. So we have conduction. So that's when I'm in contact with something. I have conduction. Convection. So that's air moving. So if the air is circulating in those cavities, which we've found is not very important actually. Sensible heat. So it's changing temperature. The droplet is evaporating. You can have radiation, so electromagnetic waves, and then there's an arrow there because as the temperature changes, if you're heating up the bottom, it becomes less dense than what's around it, and so it will actually rise, right? So you can actually get a circulation as well. We've found that conduction and evaporation are the two main factors in the droplets evaporating here in the heat transfer. So if I look at this surface on the right, this is what our surface looks like. And if only 5% of it is in contact, that's only 5% conduction, right? So any of you guys have kind of cold hands? It's not really cold in here, but a little bit. All right, so put your hand on your forearm, and if you touch it, it feels warmer, right? Unless your forearms are also freezing. But if I take it off and just put it as close as I can to my forearm, but don't actually touch it, do you really even feel any heat? It's totally different, right? So when I'm touching it, I can actually feel the heat. That's conduction. That's when they're in contact. As soon as I move it a little bit, there's a tiny little air layer in there. And it is very hard for heat to be transferred through that air relative to when I'm actually in contact with the surface. And so what we get is all these little cavities here, this 95% of what it's in contact with is like putting your hand just a millimeter away trying to warm it up by your forearm or sticking it under and sitting on them. So we might actually expect there to be less heat transfer. But what if we'll heat it up even more, right? We'll go to 150 degrees C. Maybe this is going to get a little bit better. On the smooth surface, it actually gets more exciting, right? So now it's boiling so hard, it literally removes itself from the surface. So there it goes. And then it's actually really cool. You can see as it removes itself from the surface, as soon as it's not in contact with the surface, it immediately stops that violent boiling. So it's the same idea. There's that air gap where heat is not transferred through there. So it's basically looks like it's sitting on a vapor layer. And then the superhydrophobic surface looks exactly the same. It's kind of doing nothing. But now we hopefully understand why, because now we have these air pockets in here that are reducing the heat transfer to the droplet. Now I can get to a point, even on the smooth surface, and this is as high as we could go in our lab, but we're at 220 degrees C. Here we are on the smooth surface, and you can see the droplet is kind of boiling, but it doesn't look as vigorous. The outsides are kind of waving, but it doesn't look like it's as vigorous as the earlier boiling. And what's happening is it's now right where the droplet is in contact with the surface, it immediately becomes a vapor. It's so hot that it changes phase right there, and then the droplet sits on top of a vapor layer. And as we already know, the heat isn't transferred very well through that, so then it just kind of sits there, right? And this is called the Leidenfrost effect, when it sits on a vapor layer. And the Leidenfrost point is the temperature at which that happens. Okay, so the superhydrophobic surface looks like it's doing that all the time, okay? But the smooth surface has to get pretty hot. And just since I wanted to teach you about Leidenfrost, I'm going to throw in just a quick slide of a note on the Leidenfrost effect. It's kind of fun things you can do with it. So this idea of having water immediately become vapor, you can do kind of cool things, right? So this is water going up a slope, okay? This is what it looks like if we zoom in, and what's happening is right on this surface, it's been heated up to about the temperature we were just looking at. So you can see The drop here, it's a little bit wavy, right? There's probably a little bit of boiling, but it's close to having a vapor layer underneath it. So what happens is, if you angle these the correct way, that vapor layer is going to shoot it forward as the vapor tries to escape from underneath it. So you can get droplets to go up a slope, or other important engineering applications like making a maze, right? So you can get it to go any direction you want, and I think either it gets hotter here or they've evaporated, but I can't follow them past there. But basically all of these are directing the droplets by using this interesting structure, and they're all heated, right? So it's the Leidenfrost effect, but it's not quite fully sitting on a vapor. All right, so now you know what the Leidenfrost effect is, and oh, gotta go back, sorry. Okay, and where that fits on what's called the boiling curve. Okay, so some of you guys are engineering students, you'll know what the boiling curve is, or you will soon if you don't yet. But basically, it's how much heat I can get into the liquid based on, that's the left-hand side, is heat flux, or how much heat is going in, and then the superheat is on the bottom. So that's the temperature above the critical temperature, above boiling temperature, which is just under 100 C here in Utah. So if I look at that, as I heat up, I get to a point where I have bubbles. Oh, and these should all be playing. So that looks like what you guys have oh man, there we go. And then that one actually doesn't even need to play. All right, so what you guys have already seen, where I have boiling and there's lots of motion in the bubble, or sorry, in the droplet, and there's bubbles in the droplet, and then we get more of a vapor forming because as it gets hotter and hotter, more vapor is forming, and so it kind of gets in the way and it causes the droplet to bounce. And then it's almost a complete film here, so it's barely moving. And then when it becomes a complete film, the droplet just sits and does nothing. All right, so this is the boiling curve, and it tells us what it's going to look like. When you guys are heating up water just on a pan, or in a pan on your stove, as you heat it up, you wait until it boils, right? And you wait until it reaches this nucleate boiling stage. Most of your stoves probably don't go high enough to get it to the Leidenfrost point, right? But if you were able to continue to heat it up, it would get to a point where the pool would just sit there, all right? Because it'd be sitting on a vapor layer. This looks different for each and every one of the surfaces. So if I look at the smooth surface, and this is hydrophobic, so it's still water repelling, but it's smooth. You can see the boiling curve looks like it boils less and less. If I now have 50% cavity, so 50% in contact with the surface and 50% in contact with air, I get a little bit of boiling at about 140 C, and that's it. Otherwise, it just sits there. And at 80% cavity, so it's only in contact with 20% of the surface, you can see it kind of wiggling a little bit. That's the most we get. And then by the time I get to 95% of it being cavity, it just sits there. This is really actually very important. It kind of looks cool as far as visualizing it, but it's really important because it changes this classical boiling curve that has been known for many years. The red one is the smooth surface, and it fits the boiling curve, and you can see the Leidenfrost point as it starts to level off here before it goes back up again. And then the green is the 50%, and then we're getting more and more cavity relative to surface as we go down to the purple. And you can see the Leidenfrost point has shifted, and I've pointed one out here, but it's kind of nowhere on the 95% cavity fraction surface. But basically, I don't have to heat it up as much, and I'm going to reach that point where it no longer has nucleate boiling, and it can just sit on its own vapor layer. And hopefully that makes sense because it already starts with a vapor layer, right? So it starts with a vapor layer, and there's not much heat being transferred through it through those tiny little that tiny little bit of conduction that we actually have, all right? What if I now impinge the droplet on a heated surface, right? So this top line is just high-speed imaging of a drop impinging and coming back. So this is a smooth hydrophobic surface, so it will repel it, and then super hydrophobic. So if I just look at it visually, they look very, very similar. So I might say, oh, these are almost the same thing. But if I heat up the surface, so now I've made the surface 105 degrees C, and this is a thermal imaging camera, so it's a high-speed thermal imaging. And this is, the color blue is about 35 C, and as I go to red, it goes to 65 C. And you can see as the droplet hits, it's blue and it's round. And as it spreads, it's still blue, but then it starts to become yellow and red here where it's in contact with the surface. And that continues and goes up through the droplet. And then as soon as it's removed, it's no longer being heated. But you can see all the temperature change that's occurred in that droplet. If I look on the superhydrophobic surface, it looks very similar, again, as far as spreading and bouncing. But as it spreads out, there's a tiny bit of yellow here, and then that stops. And then it's cold, and it doesn't look like it's transferring any heat, even though it's still in contact with the surface. And hopefully, I don't even have to explain why, because you were listening to the last two slides, right? So it's the same idea, right? It's hitting a surface, but it's really only in contact with 5% of the surface. I think this one's actually with 20% of the surface, right? But we can get a little bit of heat transfer here. What can happen when the drop hits, so instead of having a drop just stationary, when it hits, that's a certain amount of force coming with the droplet coming down, and it can actually force itself into the cavities. And then we'd get a lot of heat transfer right there, but then as it comes back out, you wouldn't expect to have much. A little bit more exciting, if we can move forward, is what you can't see. There we go. We heat it up even more. All right, so this is a hydrophilic surface, and I'm going to superheat it above 100 degrees C. And as it falls, hopefully this will go again. Okay, it's falling. There it goes. You can see it kind of explodes into tons of little tiny droplets. And this is called atomization. What's happening is, as it falls, okay, at least we can see it once it falls. As it falls and spreads out, there's immediate boiling, but there's nowhere for the vapor bubbles to escape, so they pop at the surface and cause all these small, fine mist of bubbles to be released. And that's called atomization. Right? So hopefully you learned something new today about atomization. Side note on atomization. This isn't the only way to get atomization. If you hear the word atomization, it's basically any fine mist or spray, taking a bulk liquid and making it a fine mist or spray. So there's, wrong way, sorry. Okay, so there's been studies where jets hitting each other can cause this spray on the outer edges of the jet, right? So now I have this fine mist. Anytime you have a spray bottle, whatever you're spraying, breath spray, whatever it is, that would be called an atomizer. It creates a fine mist. And then this is just outdoors when you have that spray in order to keep you cool on very hot days. Okay, so that's also a type of atomization. Ours is the most exciting, of course, type of atomization, and that's where you have this violent boiling and it has to escape somewhere. If I increase the temperature, the original temperature is 150 C, and the Weber number is just a relationship between basically how fast the droplet's hitting relative to how much it's going to spread, how much surface tension is going to pull it back together. So how much it's going to spread versus come back together. So as that increases, I have more momentum, so it's going to spread out further. And these are both the same Weber number, but as the temperature increases, you can see the hydrophilic surface gets pretty exciting. It goes into droplets, and then it separates, and all sorts of things happen. But on the superhydrophobic surface, if you look really closely, at 150 C, there's a tiny bit of atomization. Look really closely over here. There it is, right? That's all that happens. And the same thing was true over here. Basically, actually nothing happened over here. We didn't even see any atomization at all, right? But you can see it kind of spreads out and has these little fingers and then comes back together. Well, I no longer need to escape my vapor out of the top of the surface anymore if I have a superhydrophobic surface. I can create vapor bubbles that then just escape throughout this pillar forest. Okay, so less heat may be being transferred, but additionally, vapor can leave in a different way. It doesn't have to pop and go out the top. It can just slide out through the bottom. So very different dynamics on the two different surfaces, hydrophilic versus superhydrophobic. The really interesting thing is if I get the hydrophilic surface up to 380 degrees C, so it's the Leidenfrost point for an impinging drop, it looks very similar to a superhydrophobic surface. So watch as it hits, no atomization, you get these little fingers and it bounces back together. This is because now it is impinging on a vapor layer that looks almost exactly like a superhydrophobic surface that's mostly vapor, right? 95% vapor, now this is 100% vapor, so it actually looks very similar when I get to that point. This is just a quick map. If you look at Weber number versus the surface temperature, the blue is the region where we actually get atomization. And you can see when I have a smooth hydrophilic surface, I'll get atomization up to 350, 400 degrees C. Whereas on a superhydrophobic surface, I get a little bit of atomization in this region. So for varying Weber numbers, so how fast basically I allow the droplet to hit, up to about 225 degrees C, but that's about it, and it's just very little. All right, so I want to finish off today with a quick summary that hopefully you have learned that in order to create a superhydrophobic surface, I need a micro or nano texture, and that will help droplet mobility be enhanced. Whether or not it's rolling or jumping, whatever it is, I need a micro or nano texture. And the butterfly, nature in general, we can find lots of examples of this in nature. Additionally, the Leidenfrost point, which hopefully you know it is now, occurs sooner, right? And sometimes it's basically as soon as I heat up the surface, it seems to be in a Leidenfrost point. And then atomization is suppressed. So this middle one that isn't running, so atomization is suppressed, so we had this superhydrophobic surface and the hydrophilic surface. The superhydrophobic one didn't have much atomization, and the hydrophilic one, when I get it to the Leidenfrost point, looks almost exactly like a superhydrophobic surface in the same state. So hopefully you've enjoyed this journey, learned something about superhydrophobic surfaces, and I want you to know now you are at the forefront of knowledge in the field, right? So you can come do research in our lab, you're ready to go, but in case you didn't catch everything, are there any questions? I know no one wants to walk up to the mic, but will you? Thanks. Or are you going to carry it to him? Yeah. Oh, okay.
I'm so glad I got to come to this lecture. I thoroughly enjoyed it.
Thanks.
And by the way, you're a great teacher.
Thanks.
So you said earlier that when the droplet comes down with force, it can sometimes force itself in between the pillars or...
the ribs?
Yes, thank you. And once that kinetic energy is released, does the droplet pull itself out of the pillars, or does it stay, how would I say?
It's actually called a wetted state. So it's wetted when it stays in there, and it's called the Wenzel state. But that's a very good question, and that's actually recent research that we have done and has actually just been published. And it does actually depend on the temperature. So depending on the temperature, as it forces its way in, what happens is it overcomes the surface tension in those tiny little gaps. So it overcomes that surface tension and goes down in. And so if it's a little bit warmer, it can actually pull itself back out. But on a cooler surface, sometimes it stays stuck in there. And what happens is as the droplet comes back together, you actually see a tiny little drop that's stuck behind. And so it really does. It actually depends on temperature. At warmer temperatures, it can actually remove itself from there. And it has to do with the relative surface energy, whether or not being in that state is energetically favorable to being out of that state. Yeah.
So in theory, the small droplet that does remain, because of water's surface tension, it would attract other droplets to come follow it.
Yes.
Okay.
Yep. So this is exactly a problem that you may have and goes along the lines of the robust nature of these surfaces, right? If you impinge too hard on them and start getting droplets stuck in them, they no longer act like superhydrophobic surfaces. Yep.
Thanks so much.
Yeah, great questions.
So if you had the same amount of cavitation and the same temperature for a hydrophobic surface, would they all act the same mechanically? Or are there different types of hydrophobic surfaces?
Are you talking about the vapor bubbles, or are you talking about actual cavitation? The vapor bubbles?
Yeah, I guess.
Oh, the cavities. Sorry,
Yeah.
will you say that again, Nelson?
So if you, for example, you showed that there were like pillars and then there were like lanes and such. Do those act differently mechanically, or are they all the same?
Yes, that's a great question. They do act differently mechanically. And that's actually one of the reasons we have these very well-structured surfaces as opposed to the random structure, because we can tell how they're going to act differently. So if you think about the ribs, the ones that kind of look like lanes, The drag reduction on those in the direction of the lanes is actually quite good. If I go the other way, it's not as good.
Okay.
And then if I take the pillars, I don't get quite as good a drag reduction. And one of the interesting things is if I take those and put them really close together, right, make them really small and really close together, I can still have 95% cavity, but if they're really, really close together, the actual gaps, individual gaps, are very small. So the drag reduction isn't quite as good. But many of the other properties with water beating up and things are very similar. Yeah.
Okay.
So kind of at the macroscopic scale, when I look at that, it's more similar. Yeah.
Excellent. Thank you, Dr.
Yeah,
Crockett.
great question. Anyone else? It's not that scary.
It's pretty scary.
It's
I was only asleep for part of it.
Oh,
so I might have
thank-
missed this part.
Are you kidding me? This is, yeah, thanks, Rob.
How sensitive are the mechanical properties to contamination, for example, salt water?
So one of the other reasons we gave you these surfaces with already water in them is it's distilled water, because they can be very sensitive to things like salt water, or anything in the water can actually mechanically rub against it and tear it off. One of the biggest things as far as our surfaces go, if you leave something like salt water on there, as it evaporates, it's still going to leave the salt behind. If it's on a if it's on a horizontal surface and hasn't actually rolled off and removed itself, it can actually be pretty bad. But it can actually pick up salt if there's evaporated salt on it, if you get the droplets to roll. So I guess it depends on how you're using them, if you're allowing the drop to actually be removed or leaving it in a horizontal state. But yeah, that again speaks to the robustness. It can be a problem.
Okay, thanks.
Yeah.
And if no one else has a question of another
Okay.
unrelated, sort of unrelated. So you talked about scalability,
Uh-huh.
and then we talked about the airplane. So what kind of limits the scalability? Is it cost, manufacturing processes, or what is it?
Currently, one of the, both actually, but manufacturing processes is a big one. So I showed you what we do in the clean room to create these surfaces. I mean, we literally have a CD-sized wafer after 8 hours in the clean room. And so doing that on an airplane wing is very tough, putting that in a clean room, right? So, so actually the manufacturability and then the cost of that is also prohibitive as well. And one of the things with the sprays that are a little bit cheaper and a little bit easier, a little bit more scalable, is the robust nature. They're much less robust than some of these etched surfaces.
Right.
So,
Got it. Okay, thank
yeah.
you.
Thanks, Rob. Great. Well, thank you very much. I really enjoyed speaking with you guys. I hope that you learned something, and feel free to ask questions afterward if you have any as well. Thank you.